Okay, here we go. Take it away.
Good. Excellent. So, first of all, thanks a lot for the warm welcoming. I really appreciate being among people with the same passion and same huge telescope. It's really great. So we're going through an update from last year's presentation. Unfortunately, it's not going to be raising as much enthusiasm like, yes, there is like Chris or Dan, there is now the final project, you see it and so on. But we're getting closer, and it's giving me the chance to talk about a couple of processes and a couple of subsystems that we put some effort into in the last year. So just a brief recap. We're a small team. We're a bunch of guys in northern Italy. But I live in London. I live and work in London. So sometimes logistics is a little bit tricky, and it's a 2 hours flight, but we try to do the best, getting the best out of that. So we're going to recap just very quickly what is this project is all about. And this is a long description to say, to frame a little bit the vision that we have, and that is, we think that there's a gap between amateur astronomy and professional astronomy. You see that in diameters, but you see also in the number of people. There's a lot of amateur astronomers are taking exquisitely long hours of integration. They're taking nice pictures. So the question is, can we translate some of this energy into taking data for doing science? And this telescope is, this telescope itself is just a milestone over the bigger picture. That is, the telescope itself that we're going to talk about in a minute is a proof of concept to me, so that in the future somebody can look at that and say, oh, if I follow exactly the instruction that will be open source and available, and the processes, I can achieve the performances that these proof of concept is showing. So what are the performances? This needs to be a large telescope being able to do long exposure, basically. You can then remotize it and running a script, which are subsequent steps. But the big vision here, and I know it's very ambitious, is I'm absolutely aware of that, is we're not even getting to the final step of the project, but the vision is that, to me, success looks like a university in Bangladesh with low budget, or a group of amateur astronomers in Argentina, or a crazy guy in Australia, or a guy in the Philippines. Following the processes, they can build an object that can achieve this level of performances, right? So every single step, material, process, thing that we had conceived here, it has in mind, can the guy source the material anywhere in the world? Sometimes in Europe or in the United States, finding the supply of some items is way easier than in other parts of the world. So that means that in terms of material is way lighter in terms of cost and so on. It takes a big toll on process, because you need to make the material a bit working in a smarter way somehow. So just recapping the feature of this telescope, it's right now is an 800 millimeter. The first mirror is an 800 millimeter with a focal length that is equal to an f3.4. It is AltAz because it has to be honest. With this kind of dimension, I see that it is absolutely shared. Driver and encoders based on the SciTech 2. It needs to be transportable. In my mind, it is fairly lightweight. It is definitely the kind of stuff that you want to keep it in a certain in a place, but you can take it down and transport it in some way. To European standard, you can put it in a small van in terms of dimension, just about. We don't have these huge pickup trucks. It's got a 4 inches focuser because I say okay, let's and it has a D rotator and a guider integrated into that. All right, so another slide about what is driving us in the project is no frills, meaning that it's something really think it doesn't really add much to the project. We're not adding that. Not because it's beautiful, not because everybody's doing that. If we don't think it's really driving us closer to the success of the project, we take it off. We don't care. And every kind of decision we try, it's not easy, but we try to have it data-driven, science-driven. Sometimes it's easy, sometimes a little bit more tricky, but it is our intent. And of course, everything needs to be, as I stressed earlier, DIY friendly. So what a year of progress made is we had bits and pieces 1 year ago, and we recently were able to pull it all together. I think the picture on the right is telling two things. One is that we just made it to the ceiling. It's like it's half an inch to the ceiling. This is like we were a little bit baffled about how big it is. And yeah, the garage is getting smaller with the stuff out there. But yeah, it was a big satisfaction to see the whole thing being put together. Now, jumping to the conclusion of the presentation that we had last year, and then we're going back to another few points. Cost and timing. These are just this is my legacy from the automotive industry. I'm running a so-called bill of material. So I'm a spreadsheet listing all the components and the percentage of completion, the weight, the cost, the sourcing, and annotation, whatever it is. So right now, all these numbers do not include the mirror, because I think the mirror is a project by itself. And incidentally, we have a pin mirror now, we have another blank. I really think that it would be third time charm. Third time the charm. So we have one mirror right now. We're going to talk about that. We have already blank ready to be ground, but from experience, you need to go through few mirrors before you say, yeah, this one I'm really happy with that. That happened with our 20 inches, so we think we need to go through that. So these numbers are reflecting the telescope, but the mirror, the primary mirror, the secondary mirror included. So we are approaching the end of that. We didn't really put a lot of money, so it's not cheap, but it is. We've been very skimping on a lot of stuff. So we kept an eye on budget every single time we took a design decision. From the very beginning. Design needs to address that. And right now it is around, I think that number in pound is around 200 pounds, something like that. So every single part is not heavier than 20, 25 pounds. So you can, apart from the dimension itself, you can easily handle by a single person. So what happened in this year? So we carried out and proved one of the main processes that we developed. I'm going to talk about that later on. And these, the concept that we executed 3 major parts: the trunnion and the azimuth table. We finalized the mirror cell and the motor assemblies with the CTEC motor. So let's dive into that. a little bit more in details. So this is the process of grinding. So I need to spend few words so that we contextualize this. I call this a sophisticated version of the lazy Susan. So to me, like from a mechanical point of view, a telescope is like you need to have two bearings. Then usually the altitude is split into additional bearings, but you need to have two rolling surfaces that are at the same grade of a bearing. How can you do that on the cheap side? So I use here one of the concepts of Colin Chapman, who's the founder of Lotus Automotive, that is like, let's have one component doing two things. So integrating two functions into one component. And that component is the azimuth table. You see the picture, the upper picture is the table as it looks like upside down. So these three leg things is the tripod, and the tripod has three assemblies of bearing. There's a bigger picture here. So effectively, you have a track on the outside perimeter almost of the azimuth table that is 1.2 meter in diameter. And you have, and is resting on three pieces. So it's isostatic or isostatic. I don't know how you. So that is a perfect setup from engineering. So effectively, you have a lot of precision in the bearings. By the way, these are skate bearings, damn dirty cheap. How do you get? Where do you need to put a lot of effort here to achieve the right level of precision? Is in the track. The track needs to be basically a flat surface with, and it's just like a track of a huge bearing. How can you do that? Long pause and a lot of time execution here. So the idea here is, if you look at the schema on the diagram on the left, you have this is the table, the azimuth table, and the idea is like purely geometrical. If you can rotate something that is around an axis, you're effectively generating a surface, a track that is part of a single surface. You just need a 1 inch wide track, but you're generating that. The idea is basically, I don't take these workpiece into a CNC shop. I build a grinding machine on the workpiece. It's one off. All these items that you see here are like, I think this most expensive part is this angle grinder. All of this is $100. All right, so two bearings, two inches bearing, space, so they are a little bit more robust. This is a cart axle for carting, reused, so for free. And you have this contraption, I think is the fancy English word, where you have everything that is rotating around this axle on bearings, on fairly precise bearing, and you have an angle grinder with a diamond cup that is grinding a track that is made of carbon fiber. So like we got like 6 arches of 2 or 3 millimeter thick carbon fiber, 152 probably, $150. We glue to the bottom of the table. We put in place this stuff, and the idea was very sensitive. The idea, no, don't worry. This is the wheel. Oh. And the idea is that with this homemade grinding machine, you are generating this surface. This on paper, it was in my head, and we did a lot of preparation. How does it end up? You don't really know, because you are looking at microns. And microns, I think we looked it up yesterday, is fraction of a tau, isn't it? Exactly. So let's see if this And so the noise is annoying. It was very annoying also when I was working. This just give an idea of what you do. You just light touch going around, just not putting any kind of pressure. Just let the diamond cup grinding the carbon fiber away. And you see here that this part is ground and this is not. So you keep adjusting with two silly screws that you can have a height adjustment. On the right side, on the upper yes, that we very good. So this is this is microns, so whatever. And this was just alpha wave. But we measured that, and when we decided that it was all right, it was 91 microns total run out. That is, we checked that, yes, it's 3 to 4 tau, isn't it? Now, for a homemade contraption, that I'm pretty sure that if I'm writing it down properly and with the visual help of video, I can tell anybody in the world that has some DIY inclination that he can achieve very similar results. Right. So let's see if I can stop it because it's not really. So does it work? Those are my feet. I was meant to measure the torque that you need to calculate for the motor. As soon as you pull with a little spring, a tiny spring, it moves. So I wouldn't say frictionless, but there's really I'm very happy with the result. It wasn't really the friction what I was looking at. It was more like how accurate and flat in terms of run out the track is. And I'd say that it works. So this is an example of heavy process, dirty, cheap material. I mean, I know that carbon fiber is not considered cheap, but in the overall vision of the project, you were talking about spending 150 pounds sorry, 150 bucks of carbon fiber water jet cut, and there you go. You can do something like that. Same process. We applied it to. Sorry. I think there you go. Same process we applied to the what we call Pac-Man, that I think it's trillion, isn't it? Trillions. So what we've done here is that we pack them together. So basically they are like 4 to 5 inches in thickness. We bolted to these elements. So they are hanging by a desk. And similar concept, so you need to figure that out with a little bit of imagination. Maybe it's easier here. You have these axes. Again, you have 2 bearings here. And you basically have a grinding machine built on top of the workpiece that you need.
Testing, 1, 2.
Oh, Russ.
Hi, Russ, we can hear you. Could you please mute?
So the thing is that I could have easily taken to a CNC shop and say, look, can you figure it out? Can you just grind this stuff in a proper way, spending, I don't know, 500-600 euros and getting it done? But it wasn't in the ethos of the project. My project is like, can I tell a guy in a university from India how to do that? And I know that I can teach him how to do that. Because it's also silly simple once you think about that. So we had several tests, to be honest. This was like a long strike of failure until we find the right way to do that. So for example, at the beginning we thought about, well, let's get only a 1 inch shaft. These are already ground, so they're very precise. And glue some sandpaper around them. It didn't work. The idea originally was to use stainless strips glued to the surface here, to the outer surface, and it didn't work out. It takes too much time. You have a lot of passion to do the work with the grinder. That it was like a few millimeters thick. This is like 5 inches almost. There was no chance. So one day we thought about, well, let's use carbon fiber. Is going to be very easy to remove from with a grinding wheel. It is going to be strong enough to withstand the earth contact forces, so that it's not degrading after a while. It's going to create a bulk load of dust, while we're going to use some protection there. So we ended up using some super cheap grinding wheels. Here, the only cheat that I had is that I take it to a grinding shop and I got it dressed, so there was in coaxial to the shaft. To be honest, I think you don't need that, because somehow, given the fact that the stuff is spinning, is dressing itself against the stuff. But it was like, yeah, let's get the highest chance. Now, this is just like a funny time lapse of what we're doing. So me and my guy, you see who is the clever guy. In me, I'm using 2 COVID recycled masks, and the guy is basically on a hazmat suit. This stuff is making a lot of dust. But once you spend 10 times more in the setup and in the preparation than in the actual machine. The actual machine, once you're set up, is damn easy. That is actually studies pulling with the vacuum cleaner to get rid of most of the dust. So in this case, just the carbon fiber was applied in the standard method. We bonded, I think, a total of 8 layers of fabric, and yeah, was more than enough in terms of stock removal, because once you have the run out pre-check at the beginning is all right. Can't remember exactly what was the accuracy of the run out, but it is in the same order of magnitude, maybe a little bit better than the azimuth table. So that to me was really, we spent a lot of time of this year making these 2 parts, because was, yes, making the 2 parts, but was also validating this kind of process and making sure that anybody could do that. As stupid as we are, so if we can do that, anybody in the world can do that, isn't it? So it was interesting, and I'm very glad that we make it work, because it was not really it wasn't really given. It was one of the gambling that we were making on the project. The other sub-assembly that we finalized is the mirror cell, 27 point. It is pretty low profile. I'm using, I think, something that you then discarded some time ago when you were talking about yours. But we're using ball bearings. So the hinge bearing, it's a bearing that is I don't have a picture, I can't remember. It's not ball bearing, it's another one. But all of these, the upper triangle are able to rotate freely on a single bearing. You help me out if you remember. A spherical bearing, great. So this one is a Teflon line bearing, is not a brass or art steel. So it actually is very compliant. You can move it. It doesn't have any stiffness to that. So I think it's gonna work, but I'm happy to change the design. Again, here the reason of these wheel shapes is that first of all, I just wanted to use some FEA analysis to make the stuff as light as possible. And since this was going to be cut with a laser, with a water jet, let's say, that is coming for free.
So it's all aluminum?
It is, the top triangles are aluminum because I need a 5mm thick aluminum, always 5mm, 1/4. For the three main ones, I should have added an 8mm, so a third of an inch, and that start being fairly expensive. These parts are also like 14 inches long. They are fairly big. So I say no. Let's try to do it on the cheap side as we usually do. So that is actually just iron. Steel. I wouldn't even call it steel. Really, the lowest grade of steel that you can find. They are cut out because I wanted to match the deflection of each and every point. So effectively, all these pockets are lightweighting this stuff in order that it would match the weight of a 8mm aluminum. Instead, this one is a 4mm steel, and so it's lightweighting, and also the compliance is the same on all this point theoretically. The other thing that I would drive your attention is that this cell is floating somehow. So given the fact that I have wiffle trays, the wiffle tray needs to work properly. As far as they need always to be at the same at the center of gravity. So it needs to move during collimation with the mirror. So effectively, this is hinged on top of the lower frame that we call the H frame. It's actually more like a two-step ladder, to be honest. And it is hinged in the upper side here, and there are 2 points here. Unfortunately, I don't have a nice picture of that, but there are actually two motors with 212 motors with a gear reduction. So effectively, the idea is that once you are looking at your eyepiece or sitting your in front of your computer, you can actually you collimate the primary only with electrically. It works. It's the fact that there's a lot of torque in those motors, and it's not much of a weight of the mirror. But so, what's next? How are we doing with time?
You're good.
Excellent. So I have only few other slides. Motor assembly. I think this is just give me the chance to speak about the fall we're trying to fight off, and is backlash. So the entire drive system is conceived to either avoid or having the lowest backlash that you can think of. So it is in total, I think, is a 9,000 to 1 ratio. Most of that is achieved by I'm not touching this anymore. Okay, by friction drive. So the perimeter of the trunnions are rolling on ground bars. I think we're all familiar with this concept. And the same concept that we've seen previously on the azimuth table. 2 of the assemblies are free to roll. The third one is motor driven. So it's actually again a 60 to 1 ratio right at the beginning. And so, for example, this assembly on the right is for the altitude movement. So this is just a kind of a mock-up, but you might think that it's going to be put in this position. And I opted for a harmonic drive. This is 100 to 1. Of course, it's cheap because it's coming from Taiwan, coming from an unknown robot, I think. So I got it, crossing my finger. I stripped it off completely, replaced the bearings, and then put it back together, degrease and clean and put in the. So it's working absolutely fine. And the other point is that no disrespect here, I took away the gear head on top of the Cytec motor. It's like almost a 10-to-1, and there is like 3 or 4 gears. There's quite some backlash compared to what we're trying to achieve. So took it off, we put and we replace it with a pulley. Here what you see here that is missing is a tensioner. So again, it's not a zero backlash system, but it is as close as I think you can get to within a certain kind of budget. So this one is the azimuth and slots in basically in one of the legs, because one of the assembly of the roller assembly is actually driven directly out of this, if it makes sense.
Isn't it Marcus?
Why not? Thank you.
Thank you.
So what is next? We're getting to the last part, and it's going to be a little bit of preaching here. So it's like I'm looking from an engineering point of view to a telescope. I think it's very rewarding because it's a tricky structure. Let me get to that in a second. First of all, is that I was bragging earlier that I want to be data or science driven in all of our technical decisions. A way to do that is using FEA, finite element analysis, and you can use that for a lot of stuff. Now, this is clearly something that I've used at work for many years. Not me personally. I'm awful at that. There's a lot of smarter people than me that are using these programs. I'm just fairly good at interpreting the result and putting corrective action in place. But the 3 areas that you can use this stuff is basically deflection analysis. So like this is like when the whole thing is pointing 45 degrees, for example, how much does basically the secondary mirror moves out of the axis of the primary. And you can actually, funny enough, you can actually engineer compliance so that the secondary is going to move no matter what, small or big is going to move. In our case, it's like I think 0.15 millimeters. Again, sorry for that. I don't know how much is it's a tiny amount, but you can also put compliance in the supporting frame of the mirror, so that gives up as well, and it gives up in the same direction. So it's actually start pointing slightly toward again the center of the secondary mirror. Now we are talking about actually trying to minimize everything and using this kind of tool in order to know where you're going to and having an idea if that is too much or is good enough.
What software were you using?
We use different kind of software, ANSYS usually, and Nastron, I think at the very beginning. But the FreeCAD, that is free, there's very similar capabilities.
That's what I use.
It's a little bit more cumbersome to make it work, but I use that too, to be honest. Now, stress analysis, why you bother to see what are the stress in a telescope? The reason is that, and this is an example, it's perfectly describing how you can put that at work for you. Like red is where there are the highest stresses in the telescope. Blue is where you basically do not have stress. So from engineering point of view, that means to any engineer would mean one single thing: take material off with the blue part, because they're not doing anything effectively. So that's the reason why if you see the picture of the actual telescope, we start carving out bits and pieces in order to save weight from areas that actually do not contribute at all, or very small contribution to the structure of the telescope. Why we're doing that? Why I'm so obsessed with lightweight? Because it's easier to transport, fair enough. But there's a much more important element here, is that, and is related to the dynamic analysis, and I get into that in a second. But first of all, to me, it's like, why a telescope is a very interesting engineering structure. I thought long about that, and I can't really think about any other object that is not designed for to failure. Let's put it this way: you design an elevator. The wire is like, do your calculation, maximum load is going to break with the weight of 10 people, and then you add your safety margin or safety coefficient. 99.9% of the engineering world, of the start cars, even the table to an extent, is like, even when the case of a laptop is like the case where you are coming to break in the component, and then you're adding your safety factor. And it can be in an aircraft is very small, otherwise it won't take off. In an elevator is huge, in a car is different. So, but that is your, for an engineer, is the goal. And thinking about where it's gonna break, where's the yield stress, and then playing with that the way you want. The telescope, the most stressed part, the one, for example, that in red there, I think they're 1,000 times less stressed than the breaking point. So it's completely different approach. And the parameter that makes all of these sense is actually a combination of two different engineering parameters. One is weight, and the other one is stiffness. So, and they are not always playing in your favor every time. You need to be quite smart about that. And just for example, a quarter-inch bolt, for example, to talk about stresses and so on, you can hang a European car and it's not going to break. I think you're going to need a 1/3 inch for a pickup truck. But there's a lot of the material that we're using, and it can withstand stresses that a telescope will never ever see. So the way to think about conceptualizing the design of a telescope is completely different. I've seen a lot of people using the wrong mindset and approaching stuff, and usually it's taking you to over-engineer, over-design parts. And when it comes to a structure like that, you maybe make the top of the telescope heavy, and you're getting into trouble that the dynamic analysis is going to show in a second. So I'm just getting my preach, and now we're going to have a crash course, a 30-second crash course in the dynamic analysis from engineering. The one on the left, it helps me to show you the concept of a string, of an instrument. Have you ever thought about why you're playing a note on a guitar and you're playing the same note on a piano? The note is the same, but the sound is completely different. Where does that come from? So in musicology, that term I think is timbre, and it's coming from the fact that your string has a natural frequency. So it is natural way of reacting to an external perturbation. In case of a guitar is plucking. That is like the one that is here. It is like the natural frequency, but it doesn't react just like that. It reacts in effectively an infinite number of different ways that are dictated by its geometry, basically. So effectively, timbre, so how a note sounds out of a piano and out of a guitar, is simply the fact that there are different coefficients applied to each and every of these, and they're making up the entire sound of that, of coming from that string.
So would you call it harmonics as well?
That is if you are playing guitars and you are putting your finger into one of these notes, for example, you're basically muting the first natural frequency and you're playing the first harmonic. And so there's a harmonics in engineering, there's a harmonic in playing guitar as well. Why I'm wasting your time about the guitar strings and so on? Because effectively, the string is one of the most simplified structure that you can analyze with dynamic analysis. But you can use that on any given more complicated structure. Telescope is a very interesting field to apply this kind of analysis, because it's telling you where your design is actually failing, because you have maybe a small part of the telescope that is not strong enough. And I tell you, is usually not what you think. It baffled me many times, and me and other engineers. So this is an example of the first frequency of the telescope that we put it together. This is before the correction that we put in place. So this is, you might look at this as a highly exaggerated movement if you are slightly punching the telescope. We are fairly familiar with these because when there's a little bit of wind or somebody is touching your telescope, it start vibrating. So the oscillation, the frequency of the oscillation, and now is the damping in time, it is analyzed in this way. And this is a very powerful tool to tell you what to do. So here it is like a close-up of the area that is causing the structure to have this kind of frequency. The lower the frequency, so the lower the frequency, no, I'm not gonna get too much into it, but the more energy is involved. So the first natural frequency is the one to be addressed, and it needs to be a kind of a design goal. It needs to be over a certain threshold. Either look at different white books or white paper from GMT, the VLT and so on. They are going through all these analyses big time, and it is the way they are designing the entire structure around. And just to give an example, because the higher is the weight of the structure, the lower the frequency. And for example, the VLT has, I think it has a first natural frequency of 2 or 3 hertz, is very low, but you then have active optics to deal with that. For a system like this, I really thought that we need to go over 20 hertz. So, and again, that is the idea is that is helping me to have a structure that is sound, and that it breaks the positive feedback loop. Because if you ever had in your life an experience with a driving system that is not really very accurate in tracking, sometimes is because the motor are also moving the scope, but they also the perturbation of the system. And then you have a telescope that is floppy. It will start resonating. You're not going to see that. It's not going to point in the right direction. So I got these from my job, but I've seen that all the big telescopes around the world are basically hinging their design around the dynamic analysis. Unfortunately, it's not super easy, clearly. But it's such a powerful tool to make sure that your design is good to go. I spent a year with another engineer to do the first version of the telescope. And we thought, yeah, we're good engineers. We're gonna nail it. We're running through the analysis, and we completely missed a couple of small areas that we easily addressed afterwards. And we said, now after then a year and a half, said, yeah, I think I have on my end a design that I can go back to the astronomy club and say, guys, I think this can work. Again, sorry for my preaching. This is like, I think this is the different approach that, because I've never seen it applied in amateur astronomy. I've seen it in professional observatories, but is maybe not a super simple tool, but it's so powerful to make sure that what you're gonna get is up to the task. And in this case, for being an imager and in a system with motors, and if you're in an auto guide that you're gonna have a feedback, you need to be sure that you have to avoid positive feedback, because otherwise you're not gonna have a reliable tracking. Now, I'm gonna end up very quickly now with just a few words about the mirror that to me are a project aside. So the next steps quickly are, we're gonna do the start test in a week, possibly. We're gonna silver that mirror. We're gonna start salvaging the meniscus, the Canadian meniscus, to try a second mirror. And honestly, being realistic rather than looking at negatively or positively stuff, I think we're gonna go through a third mirror as well. Worst case, we're gonna have a lot of big mirrors around that we can end out. So right now, the first mirror, we are not holding our breath, I think is the English term, because we really want to start out of enthusiasm on a 25 millimeter, so 1 inch flat blank, which is like really extremely thin now in the center. But so when it was also a good run to take the rust away of the grinding machine that we are going to use for the subsequent mirror. So to me, silvering, fast optics, and meniscus are, as a personal speculation, I think is the path for a bright future of amateur astronomy with big telescope. Silvering because you don't want to ship your precious big optics to a place and then spending a lot of money. Fast because you need to try and have a compact design. So with a bigger diameter, you need to contain your focal length. And meniscus because from an engineering point of view, it's better than a flat, is saving a boatload of hogging time. Hogging is like, it's a lot of time just to get to the curvature with the 80 grid of stuff. So all of these, I think, are very interesting things to look up in the future. The next step in terms of project, this is like the short term, is getting the secondary mirror on. We have it already. It's actually a big flat that we already had. We're gonna adapt it for the start test, and then we're gonna carve it out. I don't know, we're gonna make an elliptical secondary mirror out of that. I need to finalize the moving scenery in the transportation system. I have all the parts around. I need just to put it back together, and the feet that are coming out of that are very important. That is an easy part that can be overlooked, and is going to screw up all the robustness of the project. Start test silvering. We're going to install in the encoder, the motor assembly, and I think there's going to be a lot of debugging because the encoders are not a delicate system.
Can you expand on the motor?
Yeah. So again, how can I do an encoding system on the chip? Because like the resolution that you need is very high. You need 10, 12 million ticks per axis. And if you're buying a RAM, you know better than me. I know I didn't even dare to ask. I think it's gonna set you off 2 or 3 grand for an encoder. Is there a different way to do that?
Find one.
Yes. So I actually conceived also other more creative way to do that. But for the first step, it's what I understood is that it's fairly cheap to find readheads. And I think because salvaging yards are like CNC machine, strip it off, usually you get it with the wiring that is cut. It's fairly easy to find readheads. I got 2 read heads for 150 pounds. What is way more complicated and sometimes expensive is to find the tape. That is like a 0.2 millimeter. Sorry about that. I don't know what is in. It's a very, very thin stainless steel strip with a grating. I think is for a grating is etched first and then is gold plated. So I got a reel actually from the US. It didn't cost me that much. It was, I think, for a total of $400. So with $500-600, I have all the parts, all the hardware to make the system.
Are they absolute or
Incremental. They're incremental. So, for example, the Trunion, again, in the Colin Chapman mindset of having something doing 2 things. The surface that we generated is a perfect surface that you can lay the strip over the encoder, so that is the encoder suffers a lot if you have a run out, so that the strip is going closer or farther from the readhead, and you don't want a movable readhead. It needs to be the gap between the reader and the strip needs to be very controlled. I think it's plus and minus 1.1 millimeter. So it's very, very cheap. It's going to be part of the debugging. I took that into consideration in the design. It is going to work. Who knows? To me, it's more a matter of having the willpower to go through and plow through all the mistakes that you always making all this kind of stuff. But that is, to me, is like, how can you save money instead of spending 2-3 grand on a new encoder from Renishaw and trying to do that with parts that you can find somehow around. They're not easy to find, but you can save a lot of money for doing that. And I think that is one of the areas. The other thing, just to elaborate on your question very quickly, Renishaw as a parent company, that is I think it's a Croatian or a Slovenian company they acquired. They're not using optical encoding, just like the Renishaw that we're talking about, is the stuff that you have on your scope 2, but they're using a magnetic strip. It's very similar. It is very similar resolution, so it's sub-micron. It just suffers from hysteresis. So basically it works perfectly fine when you're tracking one direction, but when you are inverting, you might lose a little bit. So exactly. So for a professional telescope, for playing with, we'll never use that. It doesn't make any sense. But for an amateur, they can say, yeah, maybe I need to every time that I'm going completely on the other side, I need to recenter slightly. It might make sense. The RLS, I think is the name of the company, is way cheaper than it. It's like it's a 10th of what you can buy with the Renishaw. So that might be something to explore.
Yeah, some of our customers that go on our list have tried. I don't know if it was that particular magnetic encoder, but magnetic encoders suffer from cyclical error for the more than the optical one.
Yeah. To me, what I got into several phone calls with the guys, and I got a little bit technical. What I understood is that the problem is when you are reversing the motion. Somehow it's like, so it probably depends very much on what kind of observation you are planning to do. If you have a script that is taking 5-second exposure and needs to go and replace that, it's gonna probably a disaster. If that is like you have a session, you're running a script and it's like spending a lot of time on a target, then move it to another target, you have time to recenter that slightly, that might have more sense. On a longer term, and this is back to the vision of the project, this is what we're trying to do. So first of all, is really like validate the entire project from a correlation with the FEA, but it also saying, yes, this works. These are the performance you can track as long as you can, and it's gonna be all right. But from a design point of view, I have a lot of ideas to simplify even more the design, and we're gonna find a home for the telescope. Well, I'm not living there anymore, but the telescope is being built in one of the worst area, probably in Europe, like pollution and fog and so on is open. So we're gonna make sure that it's working there. And my idea is to donate it to a small observatory so that we can remotize it, and having somebody that is running some maintenance and stuff like that, and so that is the idea to for that specific telescope. The other thing is that, and again, is my vision of success, that there are going to be many replicas of that telescope. And it doesn't need to be the same thing. I see that more as a platform. You want to have it 25 inches, you want to have it 35 inches. You can scale it up and down fairly easily with a good level of confidence that is going to bring you to the result that I cannot show you today. Sorry for that. Maybe in a year time we can say, yeah, it is working. But that is the idea. I'm validating the processes to build a telescope that gives you this kind of performances. And then anybody in the world can access to open source CAD models, process description, drawing, and whatever is the support that we can give, and replicate that, or just in pure open source style, just like slightly ameliorating that, or making it slightly different for suiting for their own needs. So I think this bring me to the end. So thanks a lot. I'm putting a little bit of thought to have a YouTube page where I'm actually describing the process, and an Instagram for the various updates, apart from a couple of threads on Cloudy Nights and the British one that I can't remember exactly the name right now. So it's not a matter of, I can say, oh, I want a lot of likes. It's more a matter of I want to describe what we're doing to most people that we can, so they might be, maybe not them, maybe a friend of them, their son or someone will be interested in this project. And if we're gonna fail, I think I concluded last year in the same way. Even if we're gonna fail, I hope somebody is gonna pick that up, or even finding a little bit of seeds to take this to the next step. It's all about that. It's like a joint effort to push the envelope rather than just having the big